In this talk, I will talk about Ricci flow or manifolds with boundary. Let us first have a quick review on Ricci flow on closed manifold. Let MG0 to be a closed compact Riemannian manifold. The Ricci flow equation is defined by the following evolution equation on the metric. So ddt of the metric will be given by the negative of its Ricci curvature. This is a weakly parabolic PDE system, and the Ricci flow was first introduced by Hamilton in 1982 when he used the Ricci flow to prove that if the initial metric has positive Ricci curvature, then after rescaling, the Ricci flow will converge to a metric with constant curvature. Using that, Hamilton obtained a topological classification of all manifolds that emit a metric with positive Ricci curvature. Subsequently, Ricci flow was used to prove the long-standing Poincare conjecture, and recently, Brendel and Sheng also used the Ricci flow to prove the differentiable sphere theorem. Ricci flow has had profound applications in geometric analysis in the past 20 years. It is worth noting that all known convergence results for the Ricci flow share common essential features. In the first convergence result, which was established by Hamilton, a key ingredient is the preservation of positive Ricci curvature. Later, many more curvature conditions were found to be preserved along the flow, and using that, many convergence theorems were obtained. In higher dimensions, positive Ricci curvature is not preserved by the flow. Nevertheless, it was discovered by Brendel and Sheng that positive isotropic curvature is preserved. Moreover, some variants of the positive isotropic curvatures were also discovered, which are the PIC 1 and the PIC 2 curvature conditions. In particular, a variant of the PIC 2 condition, which is saying that the M cos R2 has positive isotropic curvature. So this curvature condition was used to prove the differentiable sphere theorem by Brendel and Sheng. And a general convergence result for the PIC1 initial metric was also established by Brendel. On the other hand, we have little knowledge on Ricci flow or manifold with boundary, even for short-time existence of solution. And we don't really know whether there are any curvature conditions being preserved along the flow. In this talk, I will mainly focus on compact manifold with boundary. A main difficulty to impose boundary conditions along the Ricci flow is due to the diffeomorphism invariance of the Ricci curvature. So the boundary condition to be imposed has to respect this feature. And in general, we do not even have short-time existence of solution given an arbitrary boundary condition. We need to study the geometry of the boundary carefully, even for well-posedness of short-time existence of solution. I will address two main questions regarding Ricci flow or manifolds with boundary. The first question will be short-time existence and uniqueness of solution. And the second question is that, are there any curvature conditions being preserved along the flow? Let's look at some past results in the direction of short-time existence. In the case of surface, Brendel had a result in 2001 in which he prescribed the boundary condition in a way that the geodesic curvature of the boundary is 0 along the flow. So the surface will have a totally geodesic boundary along the flow. In 2012, this result was generalized to the case of convex geodesic curvature of boundary. In higher dimensions, the first result concerning short-time existence of solution was done by Shen in 1996, in which he required the boundary to be umbilical along the flow. That is, the second fundamental form of the boundary has to be a constant multiple of the metric on the boundary. So, note that this setting requires the initial metric to have an umbilical boundary. Recently, in 2016, Gianniotis obtained both short-time existence and uniqueness of solution for arbitrary initial metric, where he prescribes the mean curvature and the conformal class of the boundary. Let's look at the reasons which lead to the limitations of Shen's setting. In his setting, he opposed the short-time existence by considering the strictly parabolic Ricci-Dieterk flow with a Neumann boundary condition, which is given by the umbilical condition on the boundary. So if we exploit this boundary condition in local coordinate, this will correspond to a Neumann boundary condition of the metric. And in order to apply standard parabolic theory, compatibility of the equation is required along the corner. This imposes a restriction to the initial metric G0, in which the initial metric has to be umbilical for the sake of compatibility. So my result will remove this compatibility condition. Here is my setting for Ricci flow or manifolds with boundary. In my setting, generalize that of Shen, in which it has the potential of extending the properties of preservation of curvature conditions, which is enjoyed by Ricci flow on closed manifolds, and now to the case of manifolds with boundary, as in Shen's result in which he generalized Hamilton's result. Now, let MG0 to be a compact Riemannian manifold with boundary as usual. So I will prescribe the boundary data as follows. I require the second fundamental form of the boundary to be 0 in positive time, in which the metric will have a totally geodesic boundary once the flow started. The remark is that the initial metric does not need to have a totally geodesic boundary. Whereas in Shen's case, he needs the initial metric to have a totally geodesic boundary. So my setting has removed the compatibility conditions, and this will be reflected in the short-time resistance theorem, as you will see. So this is the short-time existence of solution. Let beta to be given, which will be a Holder exponent. Then there exists a C1 plus beta diffeomorphism psi and a capital T, which depends on the C beta norm of the initial matrix G sub 0, such that there is a solution GT exists on a small time interval 0 to T, with the property that at time 0, G of 0 is given by the pullback of G sub 0 by this diffeomorphism psi. So the appearance of this diffeomorphism is due to the lack of compatibility conditions. And besides short time existence, we also have a uniqueness of solution. So suppose G1 psi 1 and G2 psi 2 are two solution pairs as in the theorem of short time existence. Then there exists a smooth diffeomorphism phi such that G2 is related to G1 by a pullback of this diffeomorphism phi. And phi also satisfies this relation. So psi 2 is the composition of phi and psi 1. So this is actually a uniqueness modulus diffeomorphism phi. And again, the appearance of this diffeomorphism is due to the lack of compatibility conditions. There are two strengths in this setting. So the first one is that since compatibility conditions is removed, so the initial metric is allowed to be arbitrary. And the second strength is that various curvature conditions can be preserved along the flow under suitable assumptions on the boundary. And here is the theorem concerning preservation of curvature conditions. So let GT to be the solution given by the previous two theorems. And then the following holds. So if we assume the initial metric to have a convex boundary, then the flow will preserve positive curvature operator, the pick 1 curvature conditions, and the pick 2 curvature conditions. And if we assume the initial metric to have a 2 convex boundary, then the flow will preserve positive isotropic curvature. And moreover, if we assume the initial metric to have a mean convex boundary, then the flow will preserve positive scalar curvature. So this setting not only give a canonical solution to Ricci flow or manifold with boundary, because there is a uniqueness result in it, and this setting also allows various natural curvature conditions to be preserved along the flow. The advantage of prescribing the boundary to be totally geodesic is that the solution can be extended smoothly to the doubled manifolds for positive time. When this is the case, many results in Ricci flow on closed manifolds can be applied as curvature conditions are preserved. So let me show you a schematic of how this is done. So we first start the Ricci flow on this manifold with boundary on a small time interval, say 0 to epsilon. And then at time epsilon, since the boundary is totally geodesic, we can double the manifold and obtain a doubled manifold M tilde. And also, the doubled metric G tilde is smooth on this doubled manifold. So G tilde epsilon is the doubled metric. And after that, we can run the Ricci flow on this doubled manifold. So we can run the Ricci flow on M tilde with the initial metric being G tilde epsilon. And note that this is a Ricci flow on closed manifold. And also the solution of this flow will preserve curvature conditions of the initial metric G0 because by our previous theorem, this solution G tilde epsilon preserve the curvature conditions of G sub 0. So by that, the Ricci flow on the doubled manifold will automatically preserve the same curvature conditions of G0. So in doing so, we can apply the result in Ricci flow on closed manifolds to our case. And after applying those results, we can cut the doubled manifold to two halves and restrict these results to the original manifold M. And then by uniqueness, this result also applies to the Ricci flow on manifold with boundary. For example, by combining the result of Brendel, we can obtain that if the initial metric G0 is pick 1 and has a convex boundary, then a solution GT will converge to a metric of constant curvature with a totally geodesic boundary after rescaling. And we can also obtain topological classification of compact manifold with which admit metrics that are picked and have two convex boundary for dimension greater than 12. Now, let me talk about the strategy for proving short-time existence of solution. We first double the manifold, and then we extend the metric and then we extend the initial metric to the doubled manifold by reflection along the boundary. And then the resulting extended metric will be just Lipschitz. And in particular, it is a merely Holder continuous metric on the doubled manifold. And then we consider the Ricci Dieterk flow. We need to first fix a background smooth metric G hat. Then we consider the Ricci Dieterk flow given by ddt of G equals negative of 2 Ricci plus the Lie derivative of G with respect to a vector field W, which is given by this form and also with initial condition G being G sub 0, which is the extended metric on the doubled manifold. So our goal is to seek a solution to this Ricci Dieterk system that is smooth for positive time and Holder continuous for all time. That is because that the initial metric is not smooth. It is merely Holder continuous. And after we get a solution to the Ricci Dieterk flow, and we also need to get uniqueness of solution to the Ricci Dieterk flow. So after we have that, we solve the ODE. So we let phi t to be the one parameter family of diffeomorphism generated by the vector field W, and once we have these diffeomorphisms, we can pull back the solution obtained by the Ricci Dieterk flow by these diffeomorphisms, and then the resulting metric will be a solution to the Ricci flow. So the main issue is to first solve the Ricci flow from Holder continuous initial data on this closed doubled manifold, and then we solve the ODE, which will generate this one parameter family of diffeomorphisms. There are some obstacles in this process of finding a solution to the Ricci flow. So the first one is that since the initial data is merely Holder continuous, classical Schauder theory does not apply. And also, since we do not have a compatibility condition. So presumably, the derivative of G blows up as t goes to 0. And also, note that the Dirac vector field W depends on the first derivative of G, which is the Christoffel symbol of G. And this is not defined up to t equals 0 because the first derivative of G will blow up as t goes to 0. So we need to think a way to overcome these obstacles. The idea to overcome those obstacles is to work in a suitable Banach space, which can deal with the blow up. So presumably, because we don't have compatibility conditions, we expect that the first derivative of G will blow up like t to a very small power as t goes to 0. And we also expect higher order derivative of G to blow up like some powers of t. So the second derivative of G will be expected to blow up like t to the power negative epsilon plus a half, which will respect the scaling of parabolic equations. So in order to deal with these phenomenon, we need to work in a suitable Banach space. In a sequel, we define a weighted norm on the tensor bundle E over M cos a time interval. So given a Holder exponent alpha and a positive real number gamma, we define a norm ck alpha sub gamma on M cos 0t as follows. So this will be the definition of this norm. And the rate here will correspond to the blow up rate of the solution. So in the norm, we first take the parabolic Holder norm on half space, and then we multiply it with a blow up rate with a blow up rate, and then we take the sup norm. And after we define this norm, we define a weighted parabolic Holder space on the space of sections of this tensor bundle E by the following. The idea to obtain short-time existence of solution to the Ricci Dirac flow is to use the Banach fixed-point theorem on the weighted parabolic Holder space that we just defined. In order to do that, we need the following estimate for the linear parabolic system. So we first consider a linear parabolic system of this form with just C alpha initial data. So for time being, I just quote the statement of this theorem. So if the term on the right hand side, if F belongs to this space, then there exists a unique solution eta to this linear system such that eta satisfies this estimate. So the C alpha norm of eta plus a weighted parabolic Holder norm for the first derivative of eta will be bounded above by the constant times the parabolic Holder norm of F and the C alpha norm for the initial data. So the important thing in this estimate is that the right hand side only depends on the C alpha norm of the initial data. Using the above linear theory, we can apply the Banach fixed point theorem to obtain short-time existence and uniqueness of solution to the strictly parabolic Ricci-Dieterk flow. It is convenient to define a Banach space to serve as a space for solutions. So we define xk alpha to be this space, such that if G lies in this space, then the C alpha norm of G and a parabolic weighted Holder norm of the first derivative of G will be bounded. To that end, we have this theorem for short-time existence and uniqueness of solution to the Ricci-Dieterk flow. So there exists a T which depends only on the manifold and the C alpha norm of the initial metric, such that a unique solution to the Ricci-Dieterk flow exists on a short-time interval 0 and t, and such that the xk alpha norm for the solution G is bounded above by a constant which depends only on the C alpha norm of the initial data. In the next few slides, I will sketch the proof of short-time existence and uniqueness of solution to the Ricci-Dieterk flow. Recall that the Ricci-Dieterk equation is given by the following evolution equation of this form. And in our case, the initial data G0 will be just C alpha on the manifold M. So if we express the Ricci-Dieterk equation in local coordinates, then we will see that it is a strictly parabolic PDE which has this form. So it has a form of ddt of G minus the trace of Hessian G with respect to G equals a quadratic term. So this term will be quadratic in the first derivative of G. And this symbol, hat of grad, represents the covariant derivative taken with respect to the background metric G hat. And our hat here will be the Riemann curvature tensor with respect to this background metric G hat as well. And in order to obtain short-time resistance and uniqueness of solution, we will apply the Banach fixed point theorem to the space xk alpha. All right, so to do that, we consider the following linear system. So ddt of eta minus the trace of Hessian eta with respect to omega equals a quadratic term in omega. So this term will have a same form to the quadratic term in the Ricci-Dieterk equation. So it will have a form of omega inverse times omega. So it will have this form. And it is quadratic in the first derivative of omega. All right. And using the linear theory, we can show that if omega is in this space, x2 alpha, then there is a unique solution eta, which also lies in the same space to this linear system. And this solution is unique. And also, the solution satisfies an estimate of this form. So the norm of eta in this x2 alpha space will be bounded above by a constant times capital T to the alpha over 2 plus the C alpha norm of the initial data G0. So this So this defines an operator R from this space to itself by setting R of omega to be the unique solution to this linear system. And observe that if we have an element in this space G such that G is a fixed point to this operator R, then G will solve the Ricci-Dieterk equation. In the next step, we define a closed subset B in the space X2 alpha by the following. And then by the estimate in here, we see that if omega is in B, then we can make R omega, we can make the X2 alpha norm of R omega to be bound above by capital A for sufficiently small t. In other words, for sufficiently small t, the image of B via R will lie inside B. And next, we can show that if omega 1 and omega 2 are two elements in B, then this inequality holds. So for sufficiently small t, this shows that R is a contraction mapping on the subset B. And this implies that R has a fixed point by the Banach fixed point theorem. So this implies short-time existence and uniqueness of solution to the Ricci-Dieterk flow. Now we have short-time existence and uniqueness of solution to the Ricci-Dieterk flow. And using that, we are going to obtain a solution to the Ricci flow by solving this ODE backward in time. So in the classical Dieterk trick, this ODE will be solved forward in time as this. And in our case, because W depends on the first derivative of G, so W depends on the Christoffel symbol of G, and the first derivative of G blows up as t goes to 0. So the vector field W is not defined at t equals 0. So that's why we cannot solve this ODE forward in time. Nevertheless, although we solve this ODE backward in time, we can still extend the diffeomorphism phi t to the whole time interval in C1 plus beta norm for all beta smaller than alpha, where alpha is the Holder exponent for the initial metric G0. Once we solve this ODE and obtain a diffeomorphism psi t, and we have on the other hand the solution to the Ricci-Dieterk flow G, then we can pull back this solution to the Ricci-Dieterk flow by this diffeomorphism to obtain a metric G tilde. And this G tilde will be a solution to the Ricci flow. And note that because phi 0 is not the identity map, the solution G tilde to the Ricci flow will have an initial condition that is different from G sub 0 by a diffeomorphism, which is an extension of this one parameter family of diffeomorphisms to time t0, t equals 0. And also in the whole construction, the solution to the Ricci flow G tilde will also lie in this space xk beta, and it also satisfies an estimate of this form. So the xk beta norm of G tilde will be bounded above by a constant which depends on the C alpha norm of of the metric G sub 0. Now we have short-time existence of solution to the Ricci flow, and to obtain uniqueness, we need the harmonic map heat flow. Given a solution Gt to the Ricci flow and a C1 plus beta diffeomorphism psi, such that it relates G0 to the initial metric G sub 0 by this relation, we consider the harmonic map heat flow associated with the metric Gt. So we consider this harmonic map heat flow. The initial data for the harmonic map heat flow will be psi, which is the diffeomorphism psi that appears in a short-time existence theorem in Ricci flow. Notice that the coefficient of this PDE goes up as t goes to 0, because if we write this term in local coordinates, the coefficient of the PDE depends on the Christoffel symbol of Gt, which goes up as t goes to 0. Nevertheless, we can still use the linear theory and the Banach fixed point theorem, as in the case as we prove the short-time existence of solution to Ricci-Dieterk flow. We can also obtain short-time existence and uniqueness of solution to this harmonic map heat flow, such that the solution of it satisfies this estimate. Note that the solution to the harmonic map heat flow will has a order regularity. We have an order better regularity than a solution to the Ricci flow. Before I sketch the proof of uniqueness of solution to the Ricci flow, let me first recall the precise statement of the uniqueness theorem. Suppose that G1 psi 1 and G2 psi 2 are two solution pairs, such that G1 and G2 belongs to the space xk beta, and psi 1 psi 2 are C1 plus beta diffeomorphism, such that Gi at time 0 is given by the pullback of G sub 0 by the diffeomorphism psi I. Then there exists a ck plus 1 diffeomorphism phi, such that G2t is related to G1t by this diffeomorphism phi. And also, psi 2 and psi 1 are also related by this diffeomorphism phi. Now I'm going to sketch the proof of uniqueness. So first, given phi 1 and phi 2 to be two C1 plus beta diffeomorphism, I let phi ti to denote the solution to the harmonic map heat flow, starting with this C1 plus beta diffeomorphism phi I. And the harmonic map heat flow is with respect to the metric GIT and G hat. Then we pull back GIT by the inverse of the solution to the harmonic map heat flow, and then we obtain two tensor HIT, and we can show that this HIT are solutions to the Ricci-Dieterk flow, such that HIT belongs to the space xk gamma, and satisfying Hi of 0 equals the metric G sub 0. Then by the uniqueness of solution to the Ricci-Dieterk flow in this space xk gamma, we have H1t equals H2t in the time interval in which they define. And this implies that both of psi it composed with the inverse of psi I satisfies the same ODE. So both of these two maps satisfy this ODE. Consequently, by uniqueness of solution to the ODE, we have this map equals this map. And by taking phi to be this map, we obtain the desired diffeomorphism, that is G2 is related to G1 by pullback of this map. And therefore, we have obtained the uniqueness of solution modulus a diffeomorphism. That is, if G1 and G2 are two solutions to the Ricci flow, then they are different by a diffeomorphism. In the final minutes of this talk, I will talk about how the flow preserves various curvature conditions. For simplicity, I only sketch the proof of preserving the pick one curvature conditions in this talk. The proofs for other curvature conditions are similar. Let's recall the statement of the theorem. So suppose that GT is the solution to the Ricci flow or manifold with boundary on this time interval under my setting, then the following holds. If we assume the initial metric to have a convex boundary, then the flow will preserve the pick one curvature condition. And we will need this result from my other paper. There is a family of smooth Riemannian metrics which approximating the matrix G0 in the C alpha norm that satisfy that G sub lambda has a totally geodesic boundary, and if G0 has a convex boundary and is pick one, then all the G sub lambda is also pick one for sufficiently large lambda. Now, let me sketch the proof of this theorem. First, we double the manifold and we extend the matrix G sub 0 and the approximating matrix G hat lambda to the doubled manifold. And G sub 0 will extend to a C alpha matrix along by reflection, while G hat lambda will extend to a C infinity matrix by reflection to the doubled manifold. That is because that G hat lambda has the property that it has a totally geodesic boundary. And by our assumptions, because G sub 0 has a convex boundary, then by the above result, the approximating matrix G hat lambda is preserve the pick one condition of G sub 0. Now, let GT to be a solution to the Ricci flow, and let phi t solve the harmonic Mappy flow, so that if we pull back GT by the inverse of this diffeomorphism phi t, then the resulting metric G tilde will solve the Ricci detect flow with initial condition G sub 0. And on the other hand, we let G tilde lambda t to be the solutions to Ricci detect flow, starting with the approximating metric G hat lambda. By our estimate concerning the solution to Ricci detect flow, we have this estimate for G hat lambda t. So it's X2 alpha norm will be bounded above by a constant, which depends on the C alpha norm of its initial condition, which is G hat lambda. And because G hat lambda converge to G sub 0 in the C alpha norm by the property of these approximating metrics, we have the following uniform estimates for sufficiently large lambda. So for sufficiently large lambda, the x2 alpha norm of G tilde lambda t will be bounded above by a uniform constant that depends only on the C alpha norm of G sub 0, but it is independent of lambda. Next, we can pick some beta, which is between 0 and alpha. And we note that the space x2 alpha is precompact in the space x2 beta by the precompactness of parabolic Holder space. Then, because G tilde lambda is uniformly bounded in this space, first we can take limits. So G hat lambda will converge to a limit G infinity as lambda goes to infinity in the space x2 beta upon passing to a subsequence by the precompactness property. Next, by the continuity of coefficients in the Ricci-Dieterk flow, the limit G tilde infinity is also a solution to the Ricci-Dieterk flow with the same initial condition, such that it satisfies this estimate. But because the solution is unique for the Ricci-Dieterk flow, we must have G tilde infinity t equals G tilde t on the entire time interval, where G tilde t is the pullback of the Ricci flow solution by the diffeomorphism which solves the harmonic map heat flow. On the other hand, since G tilde lambda t are smooth solution to the Ricci-Dieterk flow that starts with a smooth initial metric, the pick 1 condition is preserved by the Ricci flow. This implies that the limit G tilde infinity is also pick 1. And then by diffeomorphism invariance, the solution Gt to the Ricci flow is also pick 1 for each positive t. So at this point, we have preservation of the pick 1 curvature conditions. And this finishes the proof. Thank you. This is the end of my talk.